Welcome to the explainer for Section 4, Episode 4.1, Power Transformer and Line Protection. Today, we're diving straight into internal winding fault physics, going from a tiny, hidden intern fault all the way to a catastrophic tank rupture. We'll be looking at the escalating dangers lurking deep inside stationary power transformers and exactly how highly sophisticated digital protection layers jump in to stop these failures in their tracks. So, let me ask you something. If a transformer's total load current looks completely normal, does that mean it's safe from a catastrophic failure? Well, here is what a lot of folks new to transformer protection get wrong. They look at the dials, they see the total current drawn from the network looks totally unremarkable, and they just assume everything is fine. But honestly, that assumption can lead straight to a destroyed transformer. Why? Because some of the absolute worst, most destructive faults don't immediately spike your overall load current. They kind of just hide in the details. To really get why, we need to compare two very different types of faults. First, think of a bushing flashover. This is essentially an external spark jumping where it definitely shouldn't on the outside connection point. It's loud, it's visually obvious, and it usually pulls a massive amount of current right away. But then, you have an interturn fault. This is a silent, hidden short circuit buried deep, deep inside the winding coil itself. Both are terrible for the transformer, obviously, but that interturn fault, it's way more subtle at first, which actually makes it incredibly dangerous. Think about this. A single shorted turn in a winding with hundreds of turns might represent, literally, less than 1% of the total winding. Less than 1%. Yet that single short creates this tiny, low-impedance loop. And because of the magnetic flux in the core, that tiny loop circulates absolutely massive, localized currents. We're talking currents many times higher than the transformer's normal rated current. But because it's completely confined to that tiny loop, it generates intense, severe heat that is totally invisible to your standard overcurrent measurements. The big picture looks perfectly fine, but locally it's a disaster. Since standard overcurrent protection just straight up misses it, this creates what we call a localized loop trap. I absolutely love this analogy from the source material. It acts exactly like a pressure cooker with a slow gas leak. From the outside, you have no idea. The overall current looks totally normal. But inside, extreme heat and pressure are quietly building up. That intense local heating starts breaking down the winding insulation, and the process just feeds on itself until the whole thing gives way. And if it's left unchecked, this quote-unquote minor fault kicks off a terrifyingly fast escalation timeline. First, you get the interturn fault. The heat from that causes localized arcing. Then, that arcing gets so hot, it physically vaporizes the surrounding transformer oil. That vaporized oil turns into combustible gases, which accumulate incredibly fast. They build up this immense mechanical pressure inside the sealed unit, forcing the heavy steel tank to bulge and eventually violently rupture. So, yeah, this is not just an electrical nuisance. It is a direct precursor to explosions and serious fires. Literally, the only thing standing between a minor fixable fault and a totally destroyed transformer is speed. It really just comes down to the physics. Damage energy is proportional to the square of the current multiplied by time. So the thermal and mechanical stress compounds every single cycle that fault stays active. Just a tiny delay in clearing it causes a massive, disproportionate amount of damage to the windings. You have to clear this event in milliseconds, not minutes, not seconds, milliseconds. And that brings us to the real hero of the story here, TR2P-TDF, the highly sensitive differential protection stage, also known as ANSI 87T. We've talked about this function before with generator transformer blocks, but here it's applied to standalone stationary power transformers. Since the only fault-feeding source now is the connected network, this stage is designed to act as a high-speed intervention. It zeroes in on exactly what's happening inside that tank and completely ignores any outside grid issues. It is the fastest, most selective way to catch these internal faults. This specific software function actually lives inside purpose-built digital protection and control relays like the ABB RET615. Think of this device sitting in the substation as a high-speed computer with exactly one job. It constantly watches the currents, and the split second it detects the mathematical signature of an internal imbalance, it commands the massive physical breakers to trip instantly. It completely isolates the transformer from the network before our proverbial pressure cooker has a chance to explode. So how does it actually catch this? Well, whether it's an obvious external bushing flashover or one of those sneaky, deep interturn shorts, the relay relies on a beautifully simple principle. Step 1, it measures the exact current entering the transformer. Step 2, it measures the current leaving. And step 3, it compares them. If the current entering one side suddenly doesn't match the current leaving the other side by an amount diverted into a fault path, it detects that missing current, and bam, it triggers a trip. To make this work in the real world for a standard two-winding power transformer, current transformers, or CTs, are installed on both the high-voltage and low-voltage sides. They feed their data directly back into the relay. This creates a very strictly defined zone of protection. If absolutely anything goes wrong inside that specific zone, right between those sensors, it is the relay's responsibility to catch it and clear it immediately. But, differential protection doesn't fly solo. It's just one part of a layered defense strategy. Think of the differential relay as your incredibly fast reflex to a sudden acute injury, but you still have to monitor the long-term health, right? That's exactly why the system builds in secondary defenses. We're talking thermal tracking and mechanical gas monitoring, which makes sure absolutely nothing slips through the cracks. It's a comprehensive safety net for some seriously expensive hardware. Let's break down that thermal layer. So while the differential stage catches the sudden, violent faults, the T2-PTTR thermal model, or ANSI 49, is more like an athlete's heart rate recovery monitor. It tracks the slow-building, cumulative heat stress over time. This is super important because every single time the sustained hotspot temperature rises just 6 to 8 degrees Celsius above its rating, it roughly cuts the expected lifespan of the transformer's insulation right in half. So this model constantly tracks how much heat builds up and cools down to prevent long-term, irreversible aging. Then, over on the mechanical side, we have the Buchholz relay. This is such a cool physical piece of safety gear. It's basically a literal bubble detector sitting right in the pipe between the main tank and the oil expansion conservator. When internal arcing breaks down the oil like we talked about earlier, it releases combustible gas bubbles. Those bubbles naturally rise up and displace the oil inside the Buchholz float chamber. As that oil level drops, a mechanical float switch drops with it, which physically triggers an alarm or a trip command. But here is where modern digital systems get really smart and tie it all together. The state of that mechanical float switch, it's not kept in isolation. It's wired directly into the RET615 relay as a binary input. Once it's inside the relay, a specific logic block called MAGPA-PC processes that mechanical gas signal right alongside the high-speed electrical differential signals. It creates this totally unified, airtight defense system where electrical and mechanical faults are all handled in one coherent, highly reliable trip scheme. Which leaves us with one final, kind of provocative question to wrap up this explainer. What actually happens if the very digital relay meant to protect your transformer develops a silent internal hardware fault of its own? Without built-in self-supervision, how would you even know your protection was broken before it inevitably fails to stop the next tank rupture? Luckily, these relays run continuous diagnostic heartbeat checks, instantly flagging their own faults. Because in power systems, you always have to protect the protector.